Good morning, friends and dear students. It gives me immense pleasure to be here again for my course, Flight Mechanics. It is also known as Aircraft Performance. As of now, I have completed my Module 4. First module is Introduction to Flight Mechanics, in which we have covered the basics of atmosphere, different velocities, aerodynamic forces, drag polars, thrust required, power available, these things in the module 1. Then we have seen the module 2, which is the cruise performance. In the cruise performance, we have worked for the equation of motion for the cruise, where L is equal to weight, lift is equal to weight, and thrust is equal to drag. In that process, we have already started the equations for the maximum range, maximum endurance, range for the jet aircraft, range for the propeller aircraft. Same way, we have seen the range for the different conditions, different altitude, different velocities, different parameters. We have already discussed, we have solved the numericals. In module 3, we have done the climb equations, maximum climb, all the parameters we have already discussed. In the last module, that is the turning flight, we have done the equation for radius, turning radius, turning velocity, minimum turning velocity, tight radius, rate of turning. These all things we have already done, we have already covered. Now we are starting the takeoff performance. In this takeoff performance, what is the takeoff? So if the aircraft is on the runway, it is waiting here. After clearance from the ATC, pilot is giving the throttle and it is speeding on the runway, and it is going like this, and then it will roll, then it is climb like this. So this is called the takeoff. So we are going to discuss about, in this unit, maybe 4 to 5 classes, we will be discussing the takeoff and the landing performance both, because both are very much related, only their directions are different. So we will see first the takeoff performance and how aircraft is taking off. I am Dr. Yagya Dutta Dwivedhi, professor from Department of Aeronautical Engineering, Institute of Aeronautical Engineering, Hyderabad, India. In today's topic, I am going to discuss about takeoff and the landing performance. In this introduction, common characteristics, takeoff principles, takeoff phases and the ground roll distance, derivation of ground roll distance, forces during takeoff, average acceleration method. So we will see the takeoff and the landing performance. First is the introduction. In order to airborne any aircraft, first it has to take off from a ground, and then finally it has to land. So for anything, first it has to run on the ground, and from the ground it has to go up. So takeoff and landing are the two significant phases. As we have discussed earlier that we have the different phases. First one is the takeoff, then climb, then cruise, then descent, then landing. So landing and the takeoff, two are very important phases. Without this we cannot do anything. Both landing and the takeoff are accelerated flight, and speed increases from 0 to max and then max to the 0. For the takeoff, from 0 it is standing on the ground and it is going upward, so speed is increased. For the landing also, it is from high speed to the 0 speed. So both are the accelerated flight. Acceleration at takeoff is positive, and at the landing it is a negative, or it is a deceleration. Maximum engine power used for takeoff and the minimum for the landing. So for the takeoff we use the maximum power, and for the landing, due to the gravity it is falling, so we need a minimum power. In takeoff, status varies from runway to airborne, while landing from airborne to ground. Landing and takeoff have several common characteristics. They are follows. So, what are the common characteristics between landing and the takeoff? We are going to discuss in this slide. The aircraft motions in both takeoff and the landing must be accelerated. So, must be accelerated. Accelerated means it is deaccelerated also. The aircraft angle of attack in both takeoff and the landing experiences a large variation more than 10 degree. So, in the both, the angle of attack will change very much tremendously. Landing gear has a vital role in both takeoff and the landing. Several dangers threaten these two flight phases, including stall, hitting an obstacle, and the crash. The airspeed at takeoff and the landing is very low, close to stall speed, so high lift devices are employed. Two of the significant surfaces, that is cement, grass, and asphalts, is important only at the takeoff and the landing, not in other flight. The aircraft usually has its maximum weight at the takeoff, whereas it has often the lowest weight at the landing. Autopilot for takeoff and the landing not employed and reliable. So now I will discuss about the takeoff principles. Takeoff can be constituted as a flight maneuver during which an aircraft is accelerated from stop, and after rolling on the runway for a short period of time, a couple of 10 to 60 seconds, it becomes airborne and initiate climb. So here you can see that in this diagram, it is here at the zero speed. From here it is rolling here, it is ground distance from here to here. From here it start rolling, it is SG, ground roll, and it is SA, it is airborne. So it is obstacle. So clearing the obstacle. So as and when you clear this obstacle, this is some height is given, it means your aircraft is cleared. So from here in the same line, from here it will start nose up. It is called the rotation begins, and here rotation finished, and then it start accelerating in the same direction. From here it is a curvature like this. So this is the lift off here. So in this way, takeoff principle is explained here. Three major stages of the takeoff operation, that is the SG, ground roll, then SR, it is ground roll distance, rotation distance, and it is a obstacle clearance distance. So here we have ground roll or the ground run, SG, transition or the rotation, and A is airborne. So A is here is airborne. This is the transition, and this is the ground roll or ground run. So these are the three stages of the flight. Some possibilities of mishap are inoperative engines, landing gear failure, tire flattening, hitting obstacle, crosswind effect, bird strike, and aft fuselage contact with the ground. So most of the time during landing and the takeoff, these problems may arise. Some of the engine may fail. Out of two engine, one may fail. Landing gear may not work properly. Your wheel are not extracted properly. Tire is punctured. Some obstacles are on the runway, or before the runway some trees or some high buildings are there, rise building. Wind is not properly, it is not coming straight, but it is coming with some crosswind. And bird strikes are also, and fuselage contact with the ground. These things may happen during the landing and the takeoff. So this we will see here, the Lockheed Martin C-130J Hercules during A, takeoff, and B, landing. So this is the C-130J, a very big aircraft, propeller aircraft, which can land in a very rough runway. It needs very less length also. So the Hercules during takeoff and the landing. So this is the takeoff. The first case is takeoff. You can identify that it is leaving the and it is coming down. So it is a landing. So these are the two diagrams which you can see that which is the landing. During the landing, or the takeoff, your landing gears should be properly fixed. This is a propeller aircraft C-130J. It is used for defense purpose. Lockheed Martin is preparing for Indian Air Force also we have, and some other air forces of the world. They have this Lockheed Martin, which is very good aircraft for different weather, even for very high altitude like Ladakh. This can land very easily. It can take off from there with huge amount of armored vehicles and other troops and other things. So during our this operation of Galwan, this was very instrumental aircraft. By this, within no time, we can manage our border in a very high altitude and in very high terrain. Takeoff phases and the ground roll distance. So takeoff is one of the most demanding phases of the flight. The aircraft engines are typically operating at a maximum rating. Air speeds are low, so control is minimal. So this you can see here that at starting S is equal to 0 and velocity is equal to 0. Here S is equal to Sg, V is equal to Vg, and this is called the ground roll distance. Here S is equal to Sr, that is the distance, rotation distance. Here angle of attack is increased. From here it is transition distance. Here gamma is increased. Now from here to here it is climb distance to clear 50 feet obstacle. So your aircraft should be able to clear this speed. So what is the now ground roll distance? Sg. So first we have to understand here, this is the Sg. So it is the runway distance from here to here. So velocity corresponds to Sg is Vg. Vg is the lift off velocity, that is called V lift off. Corrected for the wind. Wind means Vg is equal to V lift off plus or minus V wind. Add for that. If it is a tailwind, you have to add it, and if it is the headwind, you have to subtract it. The lift off velocity is typically expressed as some factor above the aircraft stall speed. We will use that S lift off is equal to 1.1. So V lift off is equal to 1.1 of V stall. This internationally it is a recognized value. So lift off value should be more than the V stall, and it should be nearly 1.1, means 10% of the extra to the V stall. So now we will see the derivation of ground roll distance. So we can see here that ds, that is the distance, is equal to ds by dt into dt by dv into dv. ds by dt is equal to v, and dt by dv is equal to 1 by acceleration into dv. So here we can say that 1 by a v into dv. So where a is acceleration or dv by dt. Now integrating both sides from brake release to the ground roll distance. If we integrate, we will see that s is equal to 0 to s is equal to g. This ds is equal to v to 0 to v is equal to vg, 1 by a v into dv. So to integrate it, we will take two approaches during the ground roll. One, assume acceleration is constant, and two, use the numerical approach and account for acceleration changing. In either case, we will have to evaluate acceleration, which is obtained from the Newton's second law of motion. So we will see here that using Newton's second law, lift, drag, thrust and the weight are shown. Phi is the runway slope. So this we can see here. This is the runway slope here, phi. R is the reaction force, retarding force R because of the friction. So these are forces, thrust, lift and the drag. These all forces are mentioned here. So Fz in the direction vertical is equal to Maz is equal to 0. So we can see here that this is the W cos phi. This is the W cos phi. This is the force in this direction. This is the W cos phi minus L minus N. So this N is acting in the upward direction. So it is also in the same as N. So here we can write that if phi is 0, so this N is equal to, if phi is equal to very small, we can write this reaction force N is equal to W minus L. For a small angle phi, cos 0 is equal to 1, and so the retarding force then becomes this R is equal to mu N as shown here. So this R is equal to mu R into W minus L. Typical value for mu R ranges between 0.02 for a dry concrete runway and 0.3 for a very soft ground. So it is from 0.02 to 0.3 is the your friction force of the runway. So Newton's second law in the x direction to obtain an expression for acceleration during the ground roll, we can see that here that sigma fx is equal to max w by g into ax. W by g ax is equal to 1 t minus d minus w sine phi minus r. So if we assume that phi is small, so sine phi is equal to phi, and we can write here ax is equal to g by w t minus d minus w phi minus r is equal to mu r w minus L. By figure at slope 0 and no t variation with v, we can say that lift and drag start at 0. They both increase through the takeoff roll. Both forces are proportional to v square. W is a constant during the takeoff roll, ignoring fuel consumption. R decreases during the takeoff roll because the normal force N decreases as lift increases. R is 0 at lift off. Weight is equal to lift. So if you are taking off, N will be diminished. The difference between the thrust and D plus mu R W minus 1 is net acceleration force. Again, we should assume that W phi is 0. This is the direct relation. So here different, here is the weight, here is the thrust. This from here to here is T minus D plus R. Here is the D, here is R. All the parameters are mentioned in this diagram. So we will see that average acceleration method. If we assume that acceleration is constant, denoted by a bar during the takeoff roll. So here Sg is equal to 1 by a bar. V is equal to 0 to V is equal to Vg. Vg is equal to the ground roll distance from here to here. It is the Vg is a velocity. V into dV. So 1 by a V dV, V square by 2 from 0 to Vg. So Sg is equal to 1 by a V square G by 2 or V square by V square G by 2a. So this Sg is equal to V square G. It is a ground velocity divided by 2 into acceleration. So this is the ground roll distance Sg. We can find out by this method. So Sg is equal to 1 by a bar V square G by 2 is equal to V lift off plus or minus wind speed whole square by 2a. So if it is the tailwind, you take the plus. If it is the headwind, you take the minus. So note that the minus sign is used for the headwind component and the plus sign is used for the tailwind component. Putting this average value, we will get that drag average is equal to CD half rho V square average S. So D average is equal to DS is equal to 0 plus DS is equal to SG divided by 2. So we have to take the average drag. Average drag, and this we can write here CD half rho V square average drag velocity is equal to CD half rho V square S plus CD half rho V square SGS by 2. So these are the drag calculation equations by which we can find the drag of the aircraft. A headwind will reduce VG by the wind component parallel to the runway, and in a similar manner a tailwind will increase VG. Thus a headwind will decrease SG and a tailwind will increase SG. Of course, for no wind condition, Vs is equal to 0. Therefore, V average is equal to Vg by under root 2 or 0.707 V liftoff. So, next lecture we will be understanding the landing performance, phases of the landing performance, minimization of the ground roll, forces during landing, discontinued landing, procedure of discontinued landing, balk landing. These are the previous lecture, next lecture topics. Now, these are the references which I have taken. Anderson J.D. Jr., Aircraft Performance and Design, International Edition, McGraw-Hill's first edition. SL by ME, Aircraft Performance, Theory and Practice, AIA, Education Series, AIA. Any questions you can ask me in YD Dwivedhi @gmail.com. Also do like and subscribe my channel. Give comment if you feel anywhere any queries or any mistake I might have done. Please do excuse me or do pardon me and write me. I will try to correct it. Thank you very much for the joining. Please be tuned for my next lecture. Till then, goodbye. See you.
Like, share and subscribe. Hit the bell icon for more updates.